The next talk is by Eli Aljadeff from Technion, and he will speak about the polynomial identities theory and G-graded division algebras. So thank you very much, Eli.
Thank you very much. Thank you. Thank you for the invitation. It's a great honor for me to give this lecture in honor of Amitai and Doron. With Amitai, we are collaborating already several years in writing a book that was finished last year. This is with Claudio Procesi and Antonio Giambruno. So this collaboration for me was amazing for these three really amazing mathematicians. So thank you, Amitai. And I know that Antonio is here and Claudio, so thank you, Claudio and Antonio. With Doron, of course, I know about him, but yesterday was the first time that we met, and it took me 5 minutes to see your great personality. This is really impressive. So I'm really excited to give this lecture for you, Amitai, and for you, Doron. Okay, so I will start. So there will be a main part, preliminaries, main problem, and examples. And then the second part will be answer to the main problem, but there will be a construction in order to answer the main problem. So let's start with very basic things that you all know. So this is joint work with Yaakov Karasik. So we all learned that if we start, all algebras were denoted by A will be finite dimensional algebras, and if we have a script A, then will not be finite dimensional algebra. So we have A finite dimensional case-central simple algebra, and we know that extending scalars, we get matrices. So this characterizes central simple algebras. We say that central simple algebras are forms of matrix algebras. Okay, forms in the sense of the theory of descent. In particular, we know that case-central division algebras are forms of matrix algebra. They are, of course, case-central simple algebras, so they are forms of matrix algebras. Now, less obvious, but still well known, every finite dimensional simple algebra, in other words, n by n matrices, if the field is algebraically closed, has a division algebra form. Okay, so always you can find a division algebra form for matrices, and in particular, the generic object corresponding to matrices is a division algebra. Okay, so there is a way to, that I will recall it in a minute, to construct the generic object corresponding to matrices, and this problem is if we take the G-graded algebra. And by this, I want to, it's a little unstable here in China. To replace finite dimensional simple with finite dimensional G-graded simple. And by this, I mean that the product is not zero, and there are no G-graded two-sided ideals, no trivial G-graded two-sided ideals. And I want to replace division algebra forms with G-graded division algebra form. And by this, I mean non-zero homogeneous elements in D are invertible. Let me say one in parentheses that you can consider division algebras. In other words, every non-zero element is invertible, which are G-graded. Okay, this is not what I mean here. Okay, so I will say something at the end about that. So here I'm replacing division algebras by G-graded division algebras. So non-zero homogeneous elements are invertible. So if I take such a G-graded division algebra and I take the algebraic closure and I extend scalars, I get a G-graded simple algebra, exactly as in the ungraded case. And we ask in the opposite direction, does every finite G-graded simple algebra admits a form which is a G-graded division algebra? And the answer is very, very clearly no, as you will see in a little while. Okay, so we start with a G-graded simple algebra, finite dimensional, and we ask whether, like in the ungraded case, it admits a graded division algebra. So the answer is, in general, no. So the main question that we ask, which G-graded simple algebras do admit a G-graded division algebra form? Okay, this is the question. And we are going to address this question in case the characteristic is zero and the grading group is a finite group. And the reason that we restrict to that case is that our approach will be to construct the generic object that is attached to the G-graded simple algebra A. And in order to construct the generic object, we use PI theory, and we are going to use also Kemmer theory, and more specifically, G-graded Kemmer theory. And this theory we know only in characteristic zero and for G finite. This is joint work with Bello. So few words about motivation, why to talk about G-graded algebras. So group grading on central simple algebras is really the key for studying them. For example, the isomorphism, the well-known isomorphism between the Brauer group and the second cohomology group, where this is the absolute Galois group and this is the separable closure, is realized by, there are different ways to prove it. One way is to use cross-product gradings of central simple algebras. So every case central simple algebra is Brauer equivalent to a cross-product algebra. Okay, so here you have to take a Galois extension. G is the Galois group. Alpha is an element in the second cohomology group. And this is the cross product. So it is isomorphic to the group algebra as a K vector space, but you deform the product using the action. This is this T. Okay, so G acts on K. This is the Galois action. And alpha is a cycle. Okay. Another grading, which is very important, which is very, very different from the cross-product grading, is the symbol algebra grading, or the grading coming from symbol algebras. So here we take a twisted group algebra. So this is Zn cross Zn. Okay, I write it multiplicatively, but I write Zn, Zn. And alpha is an element of the second cohomology group of Zn with values that are non-zero elements in K. But the action here is trivial on K. So this is the twisted group algebra. And we know that if the nth root of unity, a primitive nth root of unity is in the base field, then perhaps one of the, or maybe the most important, or one of the most important results in Brouwer theory is that the n torsion of the Brouwer group is generated by symbol algebras. This is the famous Merkurjev-Suslin theorem. So again, here you have a grading of an algebra. And I would say one more sentence, that some of the main open problems in Brouwer group theory are related to these gradings. For example, is every Brouwer class represented by an abelian cross product? We know that it's easy to show that every Brouwer class is represented by a cross product, but is it true that G can be taken to be abelian? Okay, so this is an open question for many years. So now, before I go to the graded case, let me recall the construction of Azumaya algebras and the generic division algebras in the ungraded case. So I recall polynomial identities. So fx is the free associative algebra over f on a countable set x. Px1 to xn is a polynomial. And we say that it is a polynomial identity of A if it vanishes upon any evaluation. So for example, xy minus yx is an identity of a commutative algebra. This is the Wagner identity, okay, that is identity of 2 by 2 matrices, and the very, very well-known Amitzur-Levitsky theorem that S to n, the standard polynomial of degree 2n, is an identity of n by n matrices. And Doron mentioned the proof of Rosette, which is really a pearl. For me, it's a pearl in algebra, maybe in mathematics. The set of identities is a T ideal, is an ideal in the free algebra, and it's transformation invariant. So now we start with the matrices where F is algebraically closed. And it's almost trivial to say that Q is a field of definition for n by n matrices. This means that we can consider an algebra over the rationals and extend scalars. And of course, this is unique minimal because Q is unique minimal. So the fact that we have a form over Q already says that this is unique minimal. And now I consider the generic n by n matrices, the algebra of generic matrices over Q. Okay, so in terms of in the entries I put indeterminates, and I take the algebra over Q. Okay, I want to take the algebra over Q because I want to build an algebra that will specialize to all forms, not to all forms above a certain field, but to all forms. So equivalent, I can take the free associative algebra over Q and mod out the identities of M and Q. Okay, the identities of n by n matrices, because there is a form over Q, the identities are also defined over Q. Okay, here there is a point that if you have a form of a certain algebra over a certain field, then the identities are defined there. But sometimes the identities may be defined over a smaller field, over a field where you don't have a form. Okay? So just a remark. So we have this is the relatively free algebra over Q. And this algebra is mapped onto algebras after extension of scalars that satisfy identities that are n by n matrices, but maybe more. But we don't want more. So in order to prevent us to get more, we have to take a central polynomial. Okay, and an example is a really amazing polynomial by Regev. Okay, it's a central polynomial that gets scalar values and not all of them are zero. This was proved by the fact that it is not a zero, but that it's not an identity. It was proved by Formanek. And this polynomial, if you have such polynomial, it will vanish on n-1 matrices. And the reason that it will vanish because if you evaluate it on n-1, knowing that it is a scalar matrix and you have zero here, it must be zero. So F vanishes on n-1 matrices. And now we invert this polynomial. And so if B is an homomorphic image and not zero of this script A, then of course B will satisfy the identities of A, which are n by n matrices. But since F is an identity, the central polynomial is an identity of n-1, and it cannot be an identity of B because F is invertible, then the identities of B do not contain the identities of n-1. And this is the remarkable Artin-Procesi theorem that A must be an Azumaya algebra over its center of degree n. So this A is this curly or script A specializes to all forms of n by n matrices. And localizing the center, okay, not only inverting one center polynomial, but localizing the entire center, this is the so-called generic division algebra degree n over the rationals. Okay, the center will be much bigger. Okay, and there are many, many important questions regarding the center of this division algebra, rationality questions and so on. Okay, but we built the algebra over the rationals. Okay, now let's go to the graded case. And the first question, how G-simple algebras look like. So two examples. One is the twisted group algebra. Twisted group algebra is in fact a graded division algebra. Okay, because all homogeneous elements are invertible. The homogeneous components are one-dimensional. So this is a graded division algebra. Another example is take R by R matrices. So this is already simple and therefore G-graded simple if we can grade it. And this is an elementary grading. So we take a tuple G1 to GR of elements of G, and we put them here on top, and we put them here on the left. So if GI here and GJ here, so the EIJ is homogeneous degree GI inverse GJ. Okay, and you can check that this is a grading. The multiplication is compatible with the grading. And Bakhtiurin, Segal, Zaitsev gave a classification of finite dimensional G-simple algebras. Okay, in let's say characteristic 0 and F algebraically closed, that every G-simple algebra is a combination of this grading, which is called fine, and the grading here that I just mentioned that is called elementary. Every algebra has this decomposition. So more precisely, we have a presentation of the grading, and you can have different presentations for the same isomorphic type of the algebra. So there is an equivalence relation. So let me not say much. There is no problem about that. Okay, so I take one presentation, and so how do I take one presentation? I have to fix a subgroup of G. I have to fix a cohomology class in the twisted, okay, where H acts trivially on F, and G1 to GR is the tuple that we just mentioned. And I take the tensor product of the twisted group algebra and the matrix algebra. And now I have a basis, U sub H, the basis of the twisted group algebra, and the elementary matrices that are basis of the matrix algebra. The tensor product is the basis of the entire algebra, and the homogeneous degree of this basis element is GI inverse H GJ. So H that came from here, and EIJ is the grading that we had before. And the center was important in the ungraded theory. So here it will be replaced by the E center. The E center is just the intersection of the center with the E component. Okay? Okay. So given a G-graded simple algebra, again, finite dimensional, we want to construct a generic G-graded Azumaya algebra, script A, that maps precisely to all G-graded forms of A. So what are the main steps? We have to show the existence and find explicitly a unique minimal field of definition K for this algebra. At the beginning, I thought that this would be an easy problem, but this turned out to be maybe the most difficult problem. So K turns out to be a cyclotomic extension.
Question?
Question? Yes?
Yeah. How do you choose the subgroup H?
Any subgroup. Any subgroup. Okay? Given A, the theorem of Bakhturin, Zaitsev, and Segal says, given A, that is G simple, over an algebraically closed field, there will be a group H. You ask how to identify. Okay, in fact, this is very similar to the Wedderburn theory in the G-graded case. If you go back to the Wedderburn theory in the G-graded case, the twisted group algebra, okay, the twisted group algebra is the division algebra part, is the graded division algebra part of the entire. Okay, so what I say now, it will answer your question. Okay, so if you start with a central simple algebra, its matrices over a division algebra. So here, even in the algebraically closed field, there is a division algebra part. This is the graded division algebra. Okay. Okay. So this K, the minimal field of definition, turns out to be a cyclotomic extension of Q. The algebra may not be defined over Q. So let me say something about the field of definition. So by the universal coefficient theorem, we know that the second cohomology group, F is algebraically closed, is isomorphic to Hom, the morphisms from the Schur multiplier to F star. So our cocycle alpha corresponds to a map from the Schur multiplier to F star. H is a finite group, so MH is also finite, and the image are just roots of unity. Okay, so Schur theory will show that Q mu, if you take these roots of unity, is a minimal field of definition This is not difficult. Okay, it's a minimal field of definition for the twisted group algebra. And hence is a field of definition for the tensor product, because the matrices are always defined over Q. So if this is defined over Q mu, and this is defined over Q, this algebra will be defined over Q mu. But the surprising part is that this is not minimal in general. The matrices may lower the field of definition. Okay, so knowing the grading here, you may lower the field of definition of the algebra. And once you have a field of definition, then we construct the free associative algebra over K, free graded associative algebra. Okay, and we take the ideal of identities as in the ungraded, but now the G-graded identities. And G-graded identity means polynomials in the free algebra that you get 0 whenever you evaluate in the right homogeneous component. Okay, and so we get a T ideal, and this T ideal is defined over K because we have a form over K. And another part of the construction is to construct an E-central polynomial. So we take the Regev polynomial, but this is not sufficient, so we have to use group representation in order to construct a E-central polynomial, a graded E-central polynomial. And the theorem says that if you take the relatively free algebra, so this is the free graded algebra divided by the T ideal, and you invert this polynomial, we get a G-graded Azumaya algebra in the sense of Artin-Procesi. There are many equivalent conditions for Azumaya algebra, and some of them hold, and some of them at least do not make sense in the G-graded case for the moment. Okay, so the definition that we can use is the Artin-Procesi, that this algebra will satisfy, this algebra has the identities gamma, every non-zero homomorphic image will satisfy the identities and will not satisfy more identities. And then we have the Artin-Procesi theorem in the graded case, and this will specialize to all graded forms. If we invert the entire E-center, as we did in the ungraded case, we will obtain the generic G-graded simple algebra over K corresponding to A. And now we can ask when this is a division algebra. It is necessary and sufficient for this algebra to be a graded division algebra if there is a form which is a graded division algebra, exactly as in the ungraded case. So there are three conditions: necessary and sufficient. The group H has to be normal in G. Now, every coset has to be represented in the tuple the same number of times. By here, I make a very small assumption that the all homogeneous components generate G. Maybe you have a grading that is a kind of degenerate, and the homogeneous component do not generate G, so they generate a smaller group. Okay, so then the whole story is for the smaller group. So I can assume that the homogeneous component, the non-zero homogeneous component, generate G. Okay, and if you have that, every H coset is represented by the same number of times in this tuple. And the third condition, a little bit more complicated, the cohomology class has to be G invariant. Now, what does it mean, G invariant? G invariant means the following. We know that G acts on H, So it acts on the Schur multiplier. Okay, now we have alpha, our cohomology class that appeared in Bach-Turing Zaitsev-Segal theorem, and this corresponds to a map, right, by the universal coefficient theorem. And we take the kernel of this map. This is B alpha, and we want this B alpha to be G invariant. This is the meaning of alpha to be invariant. Okay, so these are the three. If you have these three conditions, if and only if, you get a graded division algebra, generic algebra, and this is the same as having a G-graded division algebra form. Now, we may ask, when does A admit a division algebra form, which is G-graded? This is much stronger. I want all non-zero elements, okay? But this is another story, okay? Very interesting story, and we have many results. This is together with Yaakov, Karasik, and Doron Hale, but not a full answer. Okay, so thank you very much. And again, happy birthday, Amitai and Doron.
Very much. Are there any questions?
Yeah, Eli, I have to admit I didn't quite understand everything because I don't know much about it, but my impression is it's really a very beautiful, deep theory that has gone a long way since Amitai's pioneering work. But I have something a little bit tangential. I was excited. As I told you, one of my favorite identities is Amitai-Levitsky identity, but embarrassingly, the identity for three matrices, X, Y, and Z, for 2 by 2 matrices, I have never heard of. So is that the minimal identity for 2 by 2 matrices?
Yes, in fact, the two for 2 by 2, we know, it's known, this is Rasmislov and Drensky, that the Wagner identity and the Amitai-Levitsky, or the S4, they generate the T ideal of identities, okay? And they generate. This is really impressive. For 3 by 3, we know by Kemmer that there is a finite number of generators. This is the Specht problem, or the solution of the Specht problem. But there is no set of generators. I don't even know what is a bound on the degree needed in order to generate. Maybe people from Bar-Ilan know. Okay, I always, each time that I give a lecture, I always say, maybe people from Bar-Ilan know, but because maybe some time passed and they already know. Okay, for 3 by 3. But
so for the Amitai-Levitsky for 3 by 3 involves 6 independent matrices.
Yes, Amitai-Levitsky is the unique minimal for all n by n. This was known before Amitai. This was known before Amitai-Levitsky. You cannot have a degree n minus 1 of degree 2 less than 2n. And it is easy to show that this Amitai-Levitsky is the unique one of degree 2n. This was known before, but it was not known that this was an identity.
Thank you.
What is the Regev polynomial you have mentioned?
Okay, Regev it's really an amazing polynomial that uses
I do not hear you.
I guess we lost the connection.
So it seems that there is a problem with Eli's connection. So I suggest we thank Eli again and we go on a break and then we can ask questions after the next talk. So thank you very much, Eli.